Hello everyone, thank you for watching my video today on graphing polynomial functions. We're talking about a lot of important characteristics today, but let's get started with remembering what a polynomial function is. Okay, so a function that contains only operations of adding, subtracting, and multiplication is a polynomial function. Polynomials have smooth terms and are continuous. The shape of the polynomial is affected by the degree, whether it's really an even or odd function, even or odd degree, and the sign of what we call the leading coefficient, which we discussed a little bit in our last video as well. Remember, when simplified, polynomial function is written like this: function equals something that looks like this, where n is some positive integer, and that is the degree right there. And each coefficient, these are the coefficients here. They're all real numbers. And this is the important one here, the leading coefficient. Okay? Multiplicity is a new term. We've kind of discussed a little bit here and there, but really talking a little bit deeper into it today. Multiplicity, if x minus r to the m is a factor of f, then r has what's called m multiplicity. How many times does that zero occur? If it occurs 2, 4, 6, 8, any even number of times, okay, then we say the graph of f will, some people say touch the x-axis, some people say bounce off the x-axis. Okay, I'll use both words in class when I'm teaching here, but they're both pretty much the same thing. If it's an odd zero, so if this is x minus r to the first, third, fifth, seventh, anything like that, we say the graph of f will cross through the x-axis. Let's take a look at what that means. I want to examine the graph of a couple polynomial functions as more and more fractions multiply together. So we're going away from quadratics and further along the line of third power, fourth power, fifth power, 10th power, 100th power, whatever. Okay. We can use our calculators to sketch a quick graph of each of the following functions. Okay, so if you grab your calculator, you can start putting these in one at a time. So let's start with y1. Now, x minus 1, we probably don't need a calculator for that. We know that that's just going to be a line with a y-intercept of -1 and a slope of 1. So it's going to look like that. It's a first degree, all right? So the degree is 1, which is odd, obviously. The number of x-intercepts is only going to be 1. And the number of turns, we talked about this last week, but if you're looking at your graph here, it doesn't ever turn, never goes back the way it was coming from, so it's 0. The next one has two x-intercepts at 1, 0 and -2, 0. So again, you can go ahead and use your graphing calculator. You can pause this video at any time to put these functions in your graphing calculator. And the graph's going to look something like this when you're done. So this is the first degree, this is the first degree, so if you add those together, you get second degree, which is even. There are two x-intercepts, but it only turns once. Right here. Next one has 3 x-intercepts. Okay, again, pause the video at this point. You can get the graph from your calculator. 1, 2, 3, this is a third degree, which is again an odd number. And again, there are 3 x-intercepts. Okay, and if you hopefully have a nice graph of it at this point, you should have a graph that looks something like this. It turns twice. Again, you can pause the video to put this in your calculator. Our degree is 1, 2, 3, 4. So it's a fourth degree, which is even. It has 3 x-intercepts. All right, if you have a picture of this on your graphing calculator, it should look something like this. Number of x-intercepts. Well, it crossed there 3 times. Sorry, hit the x-axis 3 times. It turns 1, 2, 3 times. And our last one here. You can pause the video again to put this into your calculator. Has two x-intercepts at 3 and -4. The degree is 2 plus 3, which is 5, which is an odd number. It only has two x-intercepts, though. All right, and then if you have a graph of this in your calculator, it should look something like this. It's not the best graph, but it looks something close to that. So how many times did it turn? Twice. So a summary, we talked about this a couple of days ago here. If you look at all these examples, the maximum number of turns, look at the degree and the number of turns. You see the pattern developing here. Okay, it's always less than a degree, but the maximum number it's going to be is 1 less than the degree. Doesn't have to be exactly 1 less than, but the most it could be is 1 less than the degree. The maximum number of x-intercepts, again, you can look at all these. Look at the degree and the x-intercepts. The number of intercepts is never higher than a degree, but it sometimes is equal. So the maximum number of x-intercepts would be equal to the degree. I guess I should probably write the degree to make this sentence sound like a good English sentence there. So the degree will be the maximum number of x-intercepts we could have. Does it have to be that many? No, it doesn't. It could be less than that, but that's the most it could be. All right, the last thing we're going to talk about here is end behavior. This is how we write end behavior in algebra. As x goes to negative infinity, what does y go to? As x goes to positive infinity, what does y go to? Okay? How do we know? We look at two things. We look at the degree and the leading coefficient. So let's start with if the degree is even and the leading coefficient is positive. Okay, so a picture of that would be something like, think about a positive even. We could think of the y equals x squared graph. All right, because this is positive 1 and this is even 2. So it's going to look like this. So what does our end behavior do? Well, as x goes to the left, y is going up. So we say it goes to infinity. As x goes to the right, y is going up. So we say this also goes to infinity. All right, what if the degree is even, but the leading coefficient is negative? So for that one, maybe we can look at the y equals negative x squared graph. That would look something like this. As x goes left, this is going down. As x goes right, this is going down. So both of our answers here are negative infinity. What about an odd degree positive? So for an example of that, we can look at y equals x cubed, right? Positive 1 x to the third power. We should know what that graph looks like. Something like that, right? As x goes left, y goes down. As x goes right, y goes up. So as x goes to the left, y goes down. As x goes to the right, y goes up. And finally, if the degree is odd, but the leading coefficient is negative, so maybe that would be y equals negative x cubed. So that's going to look something like that. As x goes to the left, y is going to go up. As x goes to the right, y is going to go down. So as x goes to the left, y goes up. As x goes to the right, y goes down. So your end behavior, you always got to think about these two words, the degree and the leading coefficient. And once you know that, you should know, well, which of these four should the graph look like? And then you can kind of picture the end behavior from there. All right, so the next slide here, we're going to determine the end behaviors of the polynomials. Number 1, as x goes left, y goes up. So that's infinity. As x goes right, y goes down. Negative infinity. Number 2, both sides here are going up. So these are both going to be infinity. Number 3, as x goes left, we go down. So negative infinity. As x goes right, it goes up, so positive infinity. A little bit harder from a function that's not a graph, but this is where that last slide comes into play. This is what we would call a negative leading coefficient even function. So we think of that, oh, well, this is going to resemble y equals negative x squared. What does negative x squared look like? This. So our end behavior is going to be down and down. Down and down. Number 5, look at the leading coefficient and degree. There's the leading coefficient and degree, right? So this is going to be a negative x to the third power, which is going to look like this. As x goes to the left, the graph goes up. As x goes to the right, the graph goes down. Seem to have forgotten to name this function. We'll call it g of x. And the next one, too, we'll call it h of x. The last one, this is a linear function, right? So you can think of that as a y equals positive x to the third power, which is going to look like that. The end behavior, at least, will look like that. Right? So as x goes to the left, this will go down. As x goes to the right, this will go up. Okay, and again, these are really just to help you with the end behavior. Okay, as the graph gets bigger and bigger, what will the graph resemble? So this all leads us into these last two problems. Here's what we want to be able to do. Okay? Here's our function. We're going to lead through all these things here, and then we'll graph it at the end. So the degree, this is a 1 here, right, is 1 plus 2. So the degree is 3. The leading coefficient, if we multiply this out, 1 times 1 is just going to be 1. So this is going to be like a y equals x to the third graph. So describe the end behavior. As x approaches negative infinity, y will approach negative infinity. As x approaches positive infinity, y approaches positive infinity. Because the graph's going to look like this. The most zeros it can have is 3. The y-intercept. So if we put 0 in for x, we're going to get 3 times negative 1 squared, which is 3 times 1, which is 3. So 0, 3. The x-intercepts are negative 3, 0, and 1, 0. Now the multiplicity. X equals negative 3 comes from here, which is a first power. So that's odd, so that will cross the x-axis. X equals 1 comes from here, which is 2, so that's even. So that will, you could say, touch or bounce the x-axis there. The number of turning points, since the degree was 2, it's 3 minus 1, which is 2. The degree was 3, so 3 minus 1 would be 2. Now we have all the information we need to graph this. Let's plot the points that we know. The y-intercept of 0, 3. X-intercepts at negative 3, 0, and 1, 0. Right? And we know it's going to start over here and end over here, thanks to our end behavior. So our graph should look something that looks like this when we're done. Okay? At this point, If you'd like to try this last one on your own, you can pause this video and try it, and then you can unpause it. We'll walk through it. If you don't feel like you're ready for that yet, we can walk through it right now. So this one is a 3 plus 1 plus 1, a fifth power. The leading coefficient will be 1 times 1 times 1, which is again 1. So this is a positive odd, which again will look like this. So as x goes to negative infinity, y goes to negative infinity. As x goes to infinity, y goes to infinity. The most zeros we're going to have is the degree, so 5. The y-intercept, if you put 0 in for that, you would get 4 cubed times negative 1 times negative 3. So that's 64 times 3, essentially, which is 192. So 0, 192. The x-intercepts would be negative 4, 0, 1, 0, and 3, 0. Their multiplicity, all right, x equals negative 4, x equals 1, and x equals 3. Negative 4 is the third power that's odd. 1 is first power that's odd. 3 is first power that's odd. So they're all odd. So in all three of them, they will cross the axis. And the turning points would be at most 4, 1 less than a degree. Okay? Now we can plot this. Let's plot the points that we know. Negative 4, 0, 1, 0, and 3, 0, and then 0, 192. We'll just put that up there. We talked about earlier, we don't really care about the y-axis where the y-axis is numbered here. The end behavior we know is going to again look like this. So if we start to draw our graph in, cross, 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 across all three of those intercepts, and there's our picture of what our graph should look like. Okay, thank you very much for watching my video today. I hope you learned a little bit about graphing polynomials, and we'll see you again soon.